Okay, so last time we saw the definition of induced representation, and we saw some properties. Yeah. So let's recall the definition. So if we are given a representation of a group G and a subgroup H, and you have a H stable subspace of V, then we say that V is induced from this representation W of H if V is the direct sum of translates of W via various left cosets. Yeah. So we define W sub G to be rho G of W, which is another subspace of V. And we observe that this rho G depends only on the left coset corresponding to G, the left coset in which this little g belongs. And then we say that V is induced from rho or V is induced from theta or W if V is the direct sum of these WG bars, yeah, which is same as WG, W sub G, which is same as image of W under this action by G. Yeah. And notationally, we called it V is in the end of GHW. So this is what it means to say V is induced from the representation W. Yeah. So today we will see that this induced representation is so given a representation of H, there exists a representation, induced representation V, which obviously contains which satisfy this property, meaning there will be so you can embed W in so W will be inside V, and this V, when viewed as a H W, will be H stable subspace of yeah. So we will see there exists such a V, and it is unique. Yeah. So the any two will be isomorphic is what uniqueness means. Okay, and then one could so induced. So this direct sum basically means that V is generated by these translates, and these translates are mutually linearly disjoint. Yeah, which is this first condition. And then one observation was that the dimension of V is same as dimension of W times G colon H. Yeah. So the index of H in G times dimension of W is dimension of. Okay, and then the properties we saw was the following. So if you have so I've written it in these terms. So if V is an induced representation of W and V prime is induced representation of W prime, then V plus V prime is induced representation of W plus W prime. Yeah, so that you can write it this way. And then if W prime is a sub-representation of W, H sub-representation of W, then and V is a induced representation from W, then the translates of W. Translates of W prime is in V. It gives you a representation. It gives you a G representation, G sub representation of V, and that is actually an induced representation of W prime. Yeah. So another way of thinking about this is that if W has a induced representation, then W prime also has an induced representation. Sitting inside. If W has an induced representation V, then W prime has an induced representation sitting inside V, if W prime is a sub-representation of W. Yeah. And then we also saw this tensor product property at the end. So if V is an induced representation of W and V prime is some other G representation, then their tensor product is of course a G representation, and that is same as the induced representation of W tensor V prime, but in this W tensor V prime, we are thinking of V prime as a H representation. Yeah, so this is, and this is H representation. So on the right, we are thinking of V prime as an H. So any G representation is naturally an H representation. Yeah? And then we induce. So what it says is that if V is an induced representation of W, then V tensor V prime is an induced representation of W tensor V prime. Okay. So these are the properties we saw, and we also saw this example. Yeah, so maybe we also saw this example that if you take KH, the regular representation of H, that's a representation of H, and if you then and it's an H stable subspace of regular representation of G, and the regular representation of G is in fact induced from the this H stable subspace. Yeah. So so in other words, induced representation of KH from H to G is same as the regular representation of G. Yeah. So induced representation of a regular representation of some subgroup is the regular representation of the emblem. This is what we saw. Yeah. So we saw it in some different different notation. I've written it in the same statement in this this notation. That is the only difference. Make sense so far? Any questions? Okay. So today, so as I said, today we will see the existence and uniqueness of it. So one proof of existence we can give from these properties as itself, and then I'll give you a direct construction at the end. So maybe first let's do proof of existence of these representation. So proof of existence of induced representation. So what we have to do? So we are given some representation, H representation of W via representation. We want to cook up a G representation, a row from G to GLV, such that W is H, and W is a H stable subspace of V. W is a H stable. So this is space of V, and rho is induced from, and a stable subspace of V with representation theta. I guess that also one should, with representation theta. So H stables, as soon as W is an H stable, it's an H representation. Yeah, so that representation should be theta, and rho is induced from theta. Yeah, so this is what we want to say. Yeah. So we will. The way I'll give you the proof using these properties will not be constructive. We'll give a construction later on. So note that every representation. So if you are given a H representation W, you can write it as direct sum of irreducible representation. Yeah. And if you can show that each irreducible representation of H has a induced representation, then you can use. Let me give numbers to them. Yeah. So then we can use 1 to show that W itself has a induced representation. Yeah. So let's call this 1. yeah, using 1. So using 1, it is enough to see that H has, so using 1, it is enough to show every enough to show the above for W irreducible. So if we show it for W irreducible, then we can use the fact that every representation is direct sum of irreducible representation and 1. Yeah. Second is now for irreducible representation, we know that every irreducible representation sits inside regular representation. Yeah. So W is in KH. Yeah. As sub-representation. Because KH is a regular representation of H, and every irreducible representation occurs here. So you can think of W as a sub-representation of KH. And then, of course, KH has an induced representation, KG. Yeah, and KH has induced representation, KG. Yeah. So this and this we know. So then by this property, which we can call, which will number 2, then W then this W has a induced representation sitting inside KG, in fact. Yeah. Hence by 2, W has a induced G representation. So which is in fact we don't need this, but we know this is in fact a sub-representation of KG. Yeah. So the way to get this induced representation is just take translates of W under the action of G on KG, G on KG and hence on W. Yeah. So it will translate W to various other subspace. Okay, so that proves it. Yeah. So we showed that every irreducible guy has an induced representation by 2, and using 2 and the fact that KG is an induced representation of KH. And once we have any representation, it's direct sum of irreducible representation, and then we use 1. So that is how you prove the existence of induced representation. Okay, so this completes the proof of existence. Yeah, uniqueness is still there. Any questions? Okay, so that was existence. So we'll do a direct construction, but let me just prove the uniqueness, and then I'll show you how to directly construct. So I alluded towards it by what we will do is take G colon H copies of W and somehow give an action. Yeah, so we'll do that after maybe proving the uniqueness. Yeah. So for uniqueness, we will need we will actually prove some sort of universal property, yeah, and use it to prove the uniqueness. Okay, so uniqueness is also not is straightforward, in fact, but maybe this may be useful, or this is more the way one should think about it, is sort of canonical. Yeah. So of property of sort of induced representation. Yeah. So let G be a group and H be a subgroup. let rho be a representation of V induced from representation theta of rho be a representation of, or rather V rho or V is a representation of G, and theta which is induced from a representation W of H given by theta, and rho prime is some other other G representation, yeah, with the underlying vector space V prime. Yeah, so V prime is some other representation. Then of course V prime is also an H representation. Any G representation is also an H representation. Now suppose you are given a equivariant map, H equivariant map from W to V prime. So W is a subspace of H stable subspace of V, right? Yeah, in particular, W is a sub H representation. So you can ask whether a linear map is H equivariant or not. Yeah, so let F be a H equivariant map from W to V prime. Then F extends uniquely to a G equivariant map from V to V prime. Yeah. So this is the property induced representation has. This is sort of the universe. So any H equivariant map from this H representation from which this induced representation comes from extends uniquely to the induced representation. Yeah. And the proof is, I mean, it's a natural statement, so the proof is also natural. So so let's try to give the definition of this map F. Yeah. So for H in H and W in so let's try to understand what this means first. Yeah. So F is a H equivariant map. What does it mean? A little f is a H equivariant map means that given H in H and W in W, f of theta H W is same as rho prime H f of W. Yeah. So so f is a H equivariant map means H dot W is same f of H dot W is same as H dot FW, which if you write it in terms of maps, you get this. Okay. So H dot W is theta H W, and then you apply F, and that should be same as H dot FW, which is same as rho prime H evaluated at FW. Okay, or in other words, F composed theta H is same as rho prime H composed. Yeah, so this is what the hypothesis tells us on F, and the other hypothesis given to us is that V is an induced representation of theta. Yeah. So what does that mean? That means that V is direct sum of W G bar in G mod H. Yeah. And remember, W G bar was just rho G of W. Where you again direct sum of G bar in G mod H, where G is some representative of this left coset G bar. Yeah, so G G is where G is some representative. So maybe you can just say any element in this left coset. So these are G bars are left cosets. Yeah, so you take any G in G bar. Okay. And it doesn't matter which G you take. So these are the two things we are given, and from here we want to define F. So to define F, it's enough to define on these pieces. Yeah. If we define it on W G bar for every left coset G bar in G bar, then of course V being direct sum of this, so will give us a map on whole of V. Yeah. So let's try to define on W G bar. Yeah. So let little w be in capital W sub G bar. Then we want to define FW. So what is FW? So you can think of it. So I want to sort of define it in some natural way. Yeah. So you can think of FW as rho G inverse W for G in in G bar. Yeah, so you take any representative of G of this G bar, left courses G bar, and then this identity holds. And then since we want this equivariant property, this rho G should come out as rho prime G. And then of course F, one would want to write F here, but that doesn't make sense. But rho G inverse W makes sense, yeah, and F of rho G inverse W makes sense because this rho G inverse W so this makes sense because rho G inverse W is in W, yeah, since W was belong to so W was in the image of rho G, yeah. So rho G inverse W will belong to our H stable subspace W, and then on that F was defined. F is given to be something. So you get F of this guy, and then this you apply rho prime G. So this is an element of V prime rho prime G. Yeah. So this is the definition. So maybe the first line was sort of trying to say why this definition is there. So so define set FW to be this guy. Yeah. So maybe let's drop this F from here, and then this will make sense better. Yeah. So FW is defined to be this. Okay. So once you have defined FW, so first of all note that this so we have made some choice here. Yeah, G in G bar. So first, yeah. So maybe I should have said this here. So first thing, so we will show that F is F extends and it is G equivariant. Both things we have to prove. But let's first prove that F is independent of the choice of G we make. Yeah. So if let's say so instead of G, if I take G times H, yes, and then we get the same guy. Yeah. So note rho prime rho prime GH. So I just have to say that if I replace G by G times H, no, so maybe I should say for H in H, note that rho prime of G times H, F rho G times H inverse of W is same as the previous expression. Yeah. So why is this? So maybe we just simplify this. So this is rho prime G, rho prime H. Yeah. And this is F of yeah, so the rho is a group homomorphism, so it comes out as rho H inverse, rho G inverse. So maybe I'll have to move a little bit. W. Yeah, but what is this? Okay, hopefully this will be enough. Okay, so so now. So remember F is H equivariant, yeah. So this rho H inverse will come out as a rho prime H inverse, yeah. So this is rho prime G, rho prime H, rho prime H inverse, F, rho G inverse W, yeah. So any and then these two cancels out. So this is again FW. Yeah. So as you can see, it doesn't depend upon which left coset you choose. Yeah, any left coset will look like G times H for some H in H. Yeah. Which representative of the left coset you take. So any other representative will look like little G times little H for some H. Yeah. So this is well defined. Now finally we want to since we have defined and yeah, so maybe here I argued since we so enough to define since V is a direct sum. Enough to define F on W sub G bar for each of these. Yeah, because any element V in V will you can uniquely write it as sum of elements in these WG bars. Yeah, and so if you know what where each of these elements go, then of course their sum will go to the sum of their images in V prime. Yeah, because F has to be linear. Yeah. So this defines F on whole of V. Now we want to show that F is G equivalent and F restricted to this trivial quotient. So F restricted to W is capital F restricted to W is little f. So let's first show that it is G equivalent. Yeah. So again, to check F is G equivalent, we only have to check on each individual pieces, right? Because F is again linear. So if it is equivalent, G equivalent on each of these pieces, then it is going to be G equivalent on the whole thing. Yeah. So let's take G in G and W in W GI bar equals rho GI. So WGI bar, remember, is same as rho GI W for some GI in GI. Yeah. So F of rho GW is by definition. So now see, we had started with W in WGI bar. Yeah. So rho GW is not going to be in the coset G corresponding to GI, but in the coset corresponding to GGI. Yeah. So this since so that is what I've written. Since rho G W belongs to WGGI, we have to use the formula for with G replaced by G times GI. Yeah. So if you do that, you'll get rho prime GGI times F of rho GI inverse G inverse rho G W. Yeah, so I'm just using this formula. Yeah, so I'm just using this formula with G replaced by GGI. Okay. Is this okay? Yeah, and then if you simplify this, this rho prime GGI is rho prime G times rho prime GI. F of rho GI inverse. So this again, this rho is a group homomorphism. So it will split into rho GI inverse, rho G inverse, rho GW. So this cancels out, and you get this, which is same as rho inverse rho prime G times FW. Yeah, because this was precisely FW. Yeah, this expression is precisely FW because W is in WGI bar. Yeah. So we saw that F is so what we have shown is that F is G equivariant for elements in WGI, each of these WGI pieces. Now, if you are given any V in V, then it will break up uniquely into sums of elements in these guys, and the action is so now you just apply G to it, and that is how it works out. Yeah. So G is a linear map. Yeah. So G dot. Maybe I'll say a one word. So now if you have V in V, then you can write V as W1 to the sum of W1 to WR. Yeah, where WI is in WGI bar. Yeah, and then of course rho G of V is so rho G, remember, is a linear map. Yeah, so this is same as rho G of WI W1 to rho G of WR. And if you apply F here, so F is linear. So you applying F is same as taking the F of the individual guy. And again, you use the fact that rho prime G is so F of rho GV is maybe I can just write the summation. Yeah, F of rho G WI. Yeah. Sum over I, which equals 1 to R. And for the individual pieces, we have already seen this is true. So this is rho prime GI of FWI, I equals 1 to R, because we have already proved this, which is, and then you use the fact that rho prime GI is a linear, rho prime, not GI, rho prime G. Rho prime G. This factor will come out with prime, yeah, because that is how the action on V prime is. And since rho prime is a linear map, this gives you rho prime G of summation. So summation FWI, but since F is linear, this is same as F of summation WI, I equals 1 to R, which is rho prime G of F of V. Yeah, so I've completed why it is enough to prove that as well. Okay. So this completes the proof that this is equivariant. Sorry. So I also have to show that that it extends F. Yeah. So note that. So F restricted to W. So what is W? W is the W corresponds to the cosets, the H coset H itself. Yeah. So you can take G to be identity. Yeah. So not the F restricted to W is evaluated at so maybe I'll write it this way. Yeah, so note that for W in W, which is W E bar, if you like, F of W is by definition rho prime E of F of rho. So since it is already in W, so we don't have to do anything. But anyway, so E inverse of W, but rho E is so these are all trivial maps. So this is F of W. Yeah. So F extends. So F extends F. And then the final thing is uniqueness. So uniqueness also you can check. Yeah. So there is only one way to do it. Yeah. So just check. Uniqueness is trivial. Also trivial. So if f prime is another such map, then it has to be, the value has to be same. I mean, there is no option, right? This is the only way you can define. Yeah. So you use the fact that both f and f prime will be G equivariant, then this is the only possibility. So I'll leave that for you to verify. Okay, so that completes the proof of this universal property. So now, sorry, so I still have to use this to prove that, before going to direct construction, I want to prove the uniqueness of the induced representation. Yeah? So maybe I'll do it here. So, proof of uniqueness of induced representation. Okay, so that means if V and V prime both are induced representation of theta, we want to show of W, then we want to show that V and V prime are isomorphic, right? So so let W be, or maybe I'll use the symbols. Yeah. So let theta from H to GLW be a H representation, and V and V prime are G representation induced from W. Yeah. So that what it means is that W you can induce. So maybe let's call it G to GLV. So maybe let's try to use less symbols. Yeah. So I will call it V and V prime as G representation induced from W. Okay. So then we want to show that V and V prime are isomorphic. So first of all, there is a map. Yeah. So since V is induced representation of W, and there is an inclusion map, and let's call it I1 from W to V prime, yeah, which is H equivariant. I mean, it's the inclusion map, and hence it has to be. And the so V prime is a G representation, and V prime is induced from W. Yeah. So the H that means V prime is an H stable subspace of since W is a H stable subspace of V prime as well. Yeah, it's a H stable subspace of both V and V prime, and V prime is induced from both V and V prime is induced from this. So so I prime extends to a G equivariant, to a unique to a unique G equivariant map. I don't know, what do we call it? Maybe phi1 from V1 to phi1 from V to V prime. Yeah, a unique G equivariant by the previous proposition. Yeah. Right. So the previous proposition tells us that we can extend this inclusion of H equivariant map to a G equivariant map from V to V prime. Is this okay? So this is like in the tensor product also we did this. So we'll and similarly, so we have to show that phi1 is an isomorphism. So I will do that. Similarly, phi2, from V prime to V is the extension. It's frozen or something. Is the extension of the other inclusion, yeah, is the extension of is the G equivariant extension of I2 from W to V, yeah. So so W to V is also this inclusion is also since W is a H stable subspace of V, this inclusion is, I don't know why I can't write it. It's again frozen or something. Yeah, it's not writing. Let me just restart this. So maybe it's some cache issue. So I hope I haven't lost anything. Okay. Can you see the screen?
No, sir.
Oh, okay. 1 second. I haven't shared. Yeah. So this phi2 is the extension of is the G equivariant extension of W to V, the inclusion, yeah, which of course is H equivariant because that is how the action on W is. And then of course one can argue that so we want to argue that phi1 compose phi2 and the other composition both are identity. Okay. Or you know, here you are in the finite dimensional case as well, so you could have argued directly maybe as well. Yeah. So that this has to be, but maybe so since it's functory is sort of everything is natural. So phi1 compose phi2 is a map of V to itself. V to V is G equivariant. Yeah. Phi2 is a map from V prime to V and is G equivariant because composition of two G equivariant maps are G equivariant. Yeah, variant. And phi1 compose phi2 restricted to W is the identity map. Yeah. So W sits inside V prime. Yeah. So is the identity map. So of course. So that tells you that phi1 compose phi2 extends the identity on W. Yeah. So So W to extends. And restricted to this is identity, and identity of V prime restricted to W is also identity. Yeah. So the uniqueness of the extension tells you uniqueness of the extension implies Phi1 compose Phi2 is identity of V prime. Yeah, and similarly Phi2 compose Phi1 will also be identity of V prime. Yeah. So this proves that that V and V prime are in fact isomorphic. Yeah, so if you get two induced representation of W, then they have to be isomorphic as representations. Okay, so Phi1 and Phi2 are G equivalent. So isomorphisms in the category of representations means these Phi1 and Phi2 are not just some vector space isomorphism, but they are G equivalent as well. Okay. So this completes the proof of existence and uniqueness of induced representation. Yeah. Okay. So now I'll give you the direct construction in the 10-12 minutes we have, and that will complete our discussion on this existence and uniqueness of induced representation. So the direct construction as a so now yeah, getting to the direct construction. So the direct construction, as I said, is what we do is take G colon H copies of maybe this wasn't a good idea. So we take G colon H copies of W and take V to be that vector space, and we'll define some action. Yeah. But we also have to make sure W sits inside it and so on. Yeah. So we will fix some representatives of all the left cosets of H in G. Yeah. So G1 to GR will be those representatives, and G1 we will fix it to be E. Yeah, the identity element. So the first left coset is H itself, and the representative we will choose for H is the identity element. Okay, and we'll use these representatives to define this G representation, the induced G representation. So now let Wi be a copy of W. Yeah, so we'll take R copies of W, which we will index it by Wi. Yeah, so they are all H so they are H modules. Yeah, so H action on each of these Wi makes sense. Yeah, and now we will take V to be direct sum of W1 to WR, but not as H. So not as H representation, but as vector space. Yeah, so maybe as vector space. So as vector space. So we don't want to make V as some, we want to make V as a G module, not as an H module, yeah. And anyway, these one of them, W1 will be an H module, but the others may not be an H module. So V is this vector space, and now I want to give we want to give a G action on V, and then which will make sure that V is an induced representation of W. Okay. So let's define V action on define a G action on V. So given G on G, I'll tell you where does a particular element of let's say Wi go. Yeah, and then once I know about one particular element, we can define it for any element. Yeah? So if G is in G and W is in and this ith, this w superscript I, that copy of w. Then what is the definition? So g times this, so wi corresponds to this gi, the quotient representative gi. Yeah. So g times gi is basically it lies in one of the left cosets. Yeah. So let's say it lies in the jth coset. Yeah. So then you can write it as gj times h, where gj was that representative we have chosen. Yeah. And h is some element of your subgroup h. Yeah. Little h. Then we define g dot w to be theta h. So theta so h acts on w. Yeah. So theta h of w, but theta h of w, you think of it as an element of wj. Yeah. So now, so you can think of theta h of w in each of these w, because all these wi's are a copy of w. Yeah. So theta h of w in wj is what you think of. Yeah. So g dot this w is that particular element of wj. Yeah. So at the moment this looks confusing, so I'll try to make it a little more transparent. Yeah. But I hope this this may look confusing. So let me just. I hope this makes sense. Yeah. So let's take v to be some element in v. Yeah. Then v we can write it as so maybe I should use some. Yeah. So v we can write it as w. Yeah. So I should yeah, maybe I will use this index. Yeah. w1 plus or maybe I'll write it as R tuple. Yeah, this is an external direct sum. So so I can also think of it as an R tuple. So W1, W2, WR. Yeah, WI belongs to WI. But each of these WI's is same as W. Yeah, so these are just copies of W. Okay. So now we want to know what. So now g dot gi is going to be so some gj. Yeah. So depending upon this I, it will. So this gj will depend upon g and g. Yeah. So maybe I should. So this ith guy will go to some ijth guy. Yeah. So if you multiply by g these cosets, then it permutes the cosets. Yeah. So maybe one can write it as yeah. So what should I write it? G and j. It will go to j, but that j ji. Yeah. So so for I it will be, so it depends. This depends on g as well, but let's not worry about it. And some h hi. Yeah. So this depends on so h and j depends upon g as well, but for a fixed g, this is what we will get. Yeah. For gi between 1 and r, and hi in h. So, and this is unique, yeah, because so g times gi will be in one of the cosets. So let's say it's in gith coset. Then there's a unique hi such that g dot gi is gj times hi. So these are all unique. Yeah, there is no choices involved here. So so the definition is g dot v is what will I do? So so this W1 will go into J1th factor. Yeah. So maybe yeah. So it doesn't help. So W1 will go in as H1 and dot W1 in the J1th factor. So maybe there is a more reasonable way of writing this down. So It's got frozen again. Yeah. J1th factor and J1th component. And so on. So this is how G dot V will act. Yeah. So basically, once I define it on each of these WJs, then the action of G, then it defines an action of G on V. So this is the action. So we still have to check that this is indeed an action of G on V. Yeah. So I've just defined what the map should be. G dot V should be this particular vector, but we have to check that this is an action. So one has to check. One has to check that G prime G dot W is same as G prime G dot W. Yeah. So once you check this, then and it is linear is okay, yeah, because H is linear and this operation just permutes these blocks, yeah, which is also a linear operation. Yeah. So linear part is okay. Once we show that this is an action, then that's it. Linear, it's an action and it's a linear map, and hence it's a representation. Okay, so one has to check this. So so maybe this I'll leave it as an exercise. Yeah. So this is not too bad. You know. So G dot Gi you got Gji dot Hi, and similarly G prime times Gi you'll get some formula, and that will be related to G prime G dot Gi. So maybe this I'll leave it as an exercise so that you check that this is indeed an action. Yeah. So once you verify this, then this gives you a linear map. Now, of course, W1 is equal to W. Yeah? Since G1. So actually all of them are copies of W, but what I meant is since G H since V viewed as a G representation, V viewed as an H representation. So what I meant is W1 is H stable. So what we want to say is W1 is H stable. Yeah, so that is the right way to say it. So note W1 as a subspace of V is H stable, because if W belongs to W1 and H belongs to H, then the action tells us that H, so what is the action? H dot, so G1 is E, yeah, so H dot E, you can think of it as, so E, so it is in the same coset, so it's E dot H, yeah, hence H dot W is just H dot is H dot W belongs to W1, yeah. So I mean H dot W is theta H dot, so maybe theta H W, which of course again belongs to W1. because this you have to think of it as in the coset corresponding to E, which is W1. So this is W1 is H table, and if you apply this so we want to show that V is induced from W. So what you have to do is check that G of the action of G on W1, the image of the action of G on W1. So claim. So maybe and this is precisely G where G belongs to G and G bar equals so the the left coset in which G belongs is Gj. Gj bars. Okay. So Gj bars are Gjs are the representatives of this left coset. So and Wj is that factor. So if you once we show that G dot W1 is this Wj, then it will follow that so then it will follow that V is induced from W. Yeah, and this we can just check. Yeah, so G dot so W1 since it's W1, so it is so we'll have to figure out what is our Gji and Hi. So here the representative G1 is E. Yeah, so it's G dot E is of course so G lies in Gj bar, so it is Gj times some H for some H in H, and hence G dot W, hence for W in W1, hence for W in W1, G dot W1, and W is theta of H W as an element of Wj. Yeah, that was the definition. If you see here, theta H of W in Wj, where and Gj is that guy. Yeah. So that proves the claim. So that tells you that if you look at the action of G on W1, it goes to these translates Wjs. Yeah, and hence V is, and since V is direct sum of these guys, V is induced. V is direct sum of Wj, J equals 1 to R. V, it is induced from theta. Okay, so I hope this direct construction is also illuminating and makes sense. Yeah, so sorry for going over, but this was a wrong place to stop. So I'll stop.